For years, interacting with a large language model meant engaging in a rigid, single-turn transaction. You type a prompt, the model outputs text, and then it goes dormant, waiting for you to tell it what to do next. This reactive architecture creates a stall in complex workflows. Because every output marks a hard stop, the model remains tethered to human oversight to bridge the gap between tasks. The Gemini 3.5 ecosystem was designed to solve this by focusing on intelligence with action. It is a framework built to maintain momentum between steps without manual reprompting. This system relies on three interconnected components: the high-speed Gemini 3.5 Flash engine, the natively multimodal Omni world model, and the continuous Spark agent framework. Together, these form an architecture capable of operating in the background. It executes multi-step workflows across extended timeframes, moving toward a model that can think and act without being asked twice. To understand how a model transitions from a conversational chatbot to an autonomous system, we have to examine the agentic stack. This involves building from the ground up through three distinct layers. Moving toward an agentic model involves specific engineering changes. Beyond scaling parameters, the developers had to rebuild how the network perceives time, handles physical reality, and manages the math of its own token consumption. The base layer of the stack is the engine. When evaluating an engine built for action, standard question and answer benchmarks are no longer sufficient. Answering a trivia question correctly does not prove a model can navigate a complex software interface. To measure multi-step execution, we isolate the agentic category in DeepMind's benchmarks. On MCP Atlas for multi-step workflows, Gemini 3.5 Flash registers 83.6%, ahead of competitors. On Toolathlon, testing real-world tool use, Flash scores 56.5%, proving it can reliably deploy external software. But raw capability introduces a serious operational problem. High-volume agentic tasks require massive token consumption. Every time an agent iterates, checks its work, and takes a new step, it burns through data, driving up API costs. We can see how Gemini 3.5 Flash addresses this by looking at enterprise data from the cybersecurity firm Armadin, which uses agents for multi-turn threat analysis. This chart visualizes their internal stress test. It shows a 42% performance increase on their multi-turn cyber benchmark, achieved alongside a 68% reduction in token use. These efficiency gains dictate how a system is deployed. When the cost per reasoning step drops, developers can scale sub-agents horizontally, running dozens of parallel processes without hitting prohibitive cost barriers. This is the result of the baseline 3.5 Flash architecture, which was designed to prioritize speed and reasoning density over raw parameter size. Intelligence is practically useless for agents if token economics prevent continuous looping. By optimizing the engine, Gemini 3.5 Flash solves the intelligence per dollar bottleneck. That engine requires inputs to act upon, bringing us to layer 2, the senses. An agent cannot effectively operate in the real world if it is forced to translate sensory data like sound and video into text. Engineering native multimodality directly into the core model has been a defining directive from Google DeepMind's leadership, shifting away from separate, specialized models. In a traditional pipeline, audio is transcribed to text, stripping away critical acoustic metadata like emotion and tone before translation. Gemini 3.5 Flash bypasses this using direct audio-to-audio processing. The neural network takes in a raw waveform and outputs a translated waveform directly. Because the processing is native, the AI retains and replicates the original speaker's exact emotional urgency and tone. This concept of native processing extends beyond audio. Google applies the same philosophy to visual reality through the Gemini Omni model. Omni functions as a world model. It possesses an inherent mathematical understanding of physical constraints, like gravity, friction, and spatial relationships. It transforms inputs across text, images, and video seamlessly. You can prompt it to edit elements within a video, and it will render those changes while maintaining strict physical consistency. This matters because an AI cannot autonomously edit a video or reliably orchestrate a physical workflow without a grounded mathematical understanding of physics. The final layer is the framework. This is where Gemini Spark operates, acting as the entity that orchestrates both the engine and the senses. The crucial difference here is persistence. Spark is a cloud-based agent. It runs continuously in the background, 24 hours a day, executing tasks even when your laptop is closed or your phone is offline. This continuous execution is enabled by Google's agentic development platform, known as the anti-gravity harness. Anti-gravity allows a primary agent to spin up multiple specialized subagents operating in parallel, connecting to external APIs. At Shopify, they deploy parallel subagents over long horizons. One parses global market data, another tracks inventory, and a third generates merchant growth forecasts. Databricks utilizes a similar structure, deploying agents to reason across massive, unorganized datasets. The agents autonomously diagnose engineering issues, retrieve real-time documentation, and propose specific code fixes. Spark integrates into workspace tools like Docs and Gmail. It connects to external services like Canva and Instacart for multi-step tool calling. The result of this framework is a complete transfer of labor. The burden of orchestration shifts from the human user engineering the perfect prompt to the agent managing its own internal reasoning loop. The engine, the senses, and the framework now operate as a single cohesive unit, processing data continuously. This architecture is the result of Google DeepMind's historical trajectory in reinforcement learning and autonomous systems. The foundation for long-horizon strategies was established during the AlphaGo matches, where AI had to plan dozens of moves ahead to achieve a distant goal. But a Go board is a highly constrained environment. Modern enterprise workflows are unconstrained, messy, and filled with unpredictable variables. Operating autonomously in that kind of reality requires flawless, long-term memory. This is where the 1 million token context windows stops being a spec sheet feature and becomes a hard technical requirement. It is the memory buffer that prevents agentic workflows from collapsing. This graphic illustrates the MRCR version 2 benchmark. It tests long context performance by hiding specific data points inside a massive array of noise. At the 1 million token scale, Gemini 3.5 Flash achieves a 26.6% pointwise recall metric, maintaining accuracy where others degrade. Precise recall over long horizons is critical. If an agent forgets a strict constraint established in Step 1 while executing Step 50, the entire autonomous loop fails due to hallucination drift. Embedding this persistent memory into the agentic stack represents a deliberate strategy to scale these models across Google's global infrastructure. Gemini 3.5 is the convergence of high-speed mathematical reasoning, native physical and audio processing, and continuous subagent frameworks. With these 3 layers integrated, the model shifts from being a conversational tool to an orchestration engine. The final result is a powerful system that seamlessly executes the world's complex workflows autonomously in the background.